Hi, my name is Muhammad Irfan bin Zaidi. So the topic that I choose is mechanism of heat transfer. What are heat transfer and thermodynamic? Heat transfers flow of heat thermal energy due to temperature difference and the subsequent temperature distribution and changes. For thermodynamic is the branch of physics that deals with the relationship between heat and other forms of energy. In particular, it describes how thermal energy is converted to and from other forms of energy and how thermal energy affects matter. Okay, type of heat transfer mechanism there are three, which is first conduction, convection, and radiation. Let's see conduction first. What is conduction? Conduction is heat transfer through stationary matter by physical contact. Heat transferred from the burner of the stove through the bottom of the pan to food in the pan is transferred by conduction. Figure 1.0. Molecules in two bodies at different temperatures have different average kinetic energies. A molecular picture of heat conduction will help justify the equation that describes it. Figure 1.0 shows molecules in two bodies at different temperatures Th and Tc. For hot and cold, the average kinetic energy of a molecule in the hot body is higher than in the cold body. If the two molecules collide, energy transfers from the high-energy to low-energy molecule. In a metal, the picture would also include free valence electrons colliding with each other and with atoms, likewise transferring energy. The cumulative effect of all collisions is a net flux of heat from the hotter body to the colder body. Thus, the rate of heat transfer increases with increasing temperature. The difference T, which is T hot minus T cold, because the number of collisions increase. With increasing area, heat conduction is proportional to the cross-sectional area. And for figure 1.1, heat conduction occurs through any material, represented here by a rectangular bar, whether window, glass, or wire-burst blubber. A third quantity that affects the conduction rate is the thickness of the material through which heat transfer. Figure 1.1 shows a slab of material with a higher temperature on the left than on the right. Heat transfers from the left to the right by a series of molecular collisions. The greater the distance between hot and cold, the more time the material takes to transfer the same amount of heat. All four these quantities appear in a simple equation deduced from and confirmed by the experiment. The rate of conductive heat transfer through a slab of materials such as the one in figure 1.22 is given by where P is the power or rate of heat transfer in watts or in kilocalories per second. A and D are its surface area and thickness as shown in figure 1.1. Temperature hot minus temperature cold is the temperature difference across the slab, and K is the thermal conductivity of the material. Table 1.5 gives respective value of thermal conductivity. More generally, we can write P equal to negative Ka dt over x, where x is the coordinate in the direction of heat flow. Since in figure 1.22 the power and the area are constant, dt over dx is constant and the temperature decreases linearly from temperature hot to temperature cold. The second mechanism is convection. In convection, thermal energy is carried by the large-scale flow of matter. It can be divided into two types. In forced convection, the flow is driven by fan, pumps, and light. A simple example is a fan that blows air past you in hot surroundings and cools you by replacing the air heated by your body with cooler air. In free or natural convection, which is the second type, the flow is driven by boiling force. Hot fluid rise and cool will sink because density decreases as temperature increases. The house in Figure 1.3 is kept warm by natural convection. Figure 1.3: How natural convection looks like. Beyond noting that the convection rate is often approximately proportional to the temperature difference, we will not do any quantitative work comparable to the formula for convection. However, we can describe convection qualitatively and relate convection rates to heat and types. Air is poor conductor, so convection dominates heat transfer by air. Therefore, the amount of available space for airflow determines whether air transfers heat rapidly or slowly. There is little heat transfer in a space filled with air, with a small amount of other material that prevent flow. Figure 1.31: Fur is filled with air, breaking it up into many small pockets. Convection is very slow here. Fur cloth and fiberglass also take advantage of the low conductivity of air by trapping it in space too small to support convection. Figure 1.31: Some interesting phenomena happen when convection is accompanied by a phase change. The combination allows us to cool off by sweating even if the temperature of the surrounding air exceeds body temperature. Heat from the skin is required for sweat to evaporate from the skin, but without airflow, the air becomes saturated and evaporation stops. Airflow caused by convection replaces the saturated air by dry air and evaporation continues. The final mechanism is radiation. The energy of electromagnetic radiation varies over a wide range depending on the wavelength. A shorter wavelength or higher frequency correspond to a higher energy because more heat is radiated at higher temperature. High temperature produces more intensity at every wavelength but especially at shorter wavelengths. Figure 1.4a: A graph of the spectrum of electromagnetic waves emitted from an ideal radiator at three different temperatures. The intensity or rate of radiation emission increases dramatically with temperature, and the spectrum shifts down in wavelength towards the visible and ultraviolet parts of the spectrum. The shaded portion denotes the visible part of the spectrum. It is apparent that the shift toward the ultraviolet with temperature makes the visible appearance shift from the red to white to blue as temperature increases. B. Note the variation in color corresponding to variation in flame temperature. Consider a silver object and a black object that can exchange heat by radiation and in thermal equilibrium. We know from experience that they will stay in equilibrium, the result of a principle that will be discussed at length in the second law of thermodynamics. For the black object's temperature to stay constant, it must emit as much radiation as it absorbs, so it must be as good as radiating as absorbing. Similar considerations show that the silver object must radiate as little as it absorbs. Thus, one property, emissivity, controls both radiation and absorption. Finally, the radiated heat is proportional to the object's surface area, since every part of the surface radiates. If you part the coals of a fire, the radiation increases noticeably due to an increase in the radiating surface area. So here is the diagram that shows us the whole picture of thermodynamics. That's the mechanism of heat transfer in thermodynamics, which is we have convection, radiation, and also conduction. By that, that's all from me. Thank you.